Seismic tomography. Seismic tomography is an imaging technique that uses seismic waves generated by earthquakes or explosions to create 2- and 3-dimensional images of Earth's interior. P, S, and surface waves can be used for tomographic models of different resolutions based on seismic wavelength, wave source distance, and the seismograph array coverage. Geoscientists use these images to better understand core, mantle, and plate tectonic processes. When energy is released from the focus of an earthquake as seismic waves that spread outward in all directions, these seismic waves travel through the Earth's interior until they reach the surface. Upon arrival at the Earth's surface, these waves shake the ground, and seismometers digitally record the earthquakes at hundreds of stations distributed on the Earth's surface all over the world. By recording the seismograms of many earthquakes, seismologists are able to create high-resolution images of Earth's interior using the methods of seismic tomography. Using the travel distance of the wave from the focus of the earthquake to the seismometer at the recording station, seismologists can calculate the average speed of the seismic waves. The speed of the seismic waves depend on the type of rock materials, the temperature of the rocks, and the stability of the area. Seismic tomography can show the structures inside the Earth that have different physical properties than the surrounding mediums, such as magma chamber. The clarity of the tomographic results is conditional upon using large number of stations and distributing them well on the ground. The good coverage of ray path gives high resolution seismic tomography results. Seismic tomography is similar to medical X-ray computed tomography, CT scan, in that a computer processes receive data to produce a 3D image, even though CT scan use attenuation instead of travel time difference. Seismic tomography has to deal with the analysis of curved ray paths, which are reflected and refracted within the Earth and potentially and certainly in the location of the Earth hypocenter. Local tomography. Local tomographic models are often based on a temporally seismic array targeting specific areas, unless in active regions with wide-ranging permanent network coverage. These allow for the imaging of the crust and upper mantle. Regional to global scale tomographic models are generally based on long wave lengths. Various models have better agreement with each other than local models due to the large feature size they image, such as subducted slab and super blooms. This model use data from both permanent seismic station and supplementary temporary arrays. Seismic tomography can resolve anisotropy, density, and bulk sound velocity. Variation in these parameters may be a result of thermal or chemical differences, which are attributed to processes such as mantle blooms, subducting slabs, and mineral phase changes. Larger scale features that can be imaged with tomographic, including the high velocity beneath continental shields and low velocity under ocean spreading centers.